Hi, this is Dr. Goldstein, and I'm going to tell you a bit about inverse functions. So first, an intuitive way of thinking about inverse functions. If f of a is equal to b, then a is equal to f inverse of b. So here, this notation, f inverse, this denotes the inverse of f. So the idea here is that the inverse function reverses the inputs and outputs. So the inverse function reverses inputs and outputs. So in other words, it undoes the original function. If A originally maps to B via F, then F inverse is going to map B back to A. And likewise, if F inverse maps B to A, then F should undo that and map A back to B. So overall, nothing changes when you do one function followed by the other function. Now, the important thing to notice is that this only works if your original function f is 1 to 1. So this only works if f is 1 to 1. And here's an example to see why that's true. So let's look at our favorite function, f of x equals x squared. And we notice that this function is not 1 to 1 because f of 2 is 2 squared, which is 4, and f of minus 2 is negative 2 squared, which is also 4. So if we wanted to define f inverse of 4, we could either have that f inverse of 4 is 2 or f inverse of 4 is minus 2, and we don't know which. And that's a problem because that means that our inverse function is not well defined. In order for a function to be well defined, each input has to go to exactly one output, and here we have two different choices for where 4 would get sent. So one way to see this is if I graph f of x equals x squared, and so here is 2, and here's minus 2, and we can see that they both go to the y value 4. And so what's going on here is that my function f doesn't pass the horizontal line test. So we fail the horizontal line test. Now, if my inverse function is going to reverse my inputs and outputs, so f inverse reverses the x and the y's, so that means that my graph for f inverse, I'll just swap my two axes. My graph for f inverse would have to look like this. So here's 2 and minus 2 on the y-axis instead of the x-axis. And we can see that if we try to compute f inverse of 4, we don't know whether to take it up to 2 or take it down to minus 2. So what's going on here? F fails the horizontal line test. F inverse fails the vertical line test. and so f inverse is not a function. So that's an intuitive description of inverse functions and an intuitive explanation of why you only have an inverse if your function is one-to-one. Let's see some explicit examples now of how to compute inverse functions. So I have f of x equals x plus 1. First, we're going to check that f is one-to-one. Then, 2, we're going to compute the inverse. So, remember, one-to-one is synonymous with the horizontal line test. And if I draw some sample horizontal lines, here's the graph of f of x, which is x plus 1. I can see visually that f passes the horizontal line test, so f is one-to-one. So I have a reasonable expectation that my inverse exists. So now, if I want to actually compute the inverse, originally we have that our output, y, is x plus 1. And we want to figure out how to send y back to x. So we want to send y back to x, i.e. we want to solve for x. So this one's pretty easy. I subtract 1 from both sides, and I end up with y minus 1 is equal to x. So if I want to reverse my function f, I take x to x plus 1. If I want to reverse that, I would subtract 1 instead. So f inverse of, we'll call it y, is y minus 1. Now, we don't usually do this. We don't usually write a y. We usually write f inverse of x is x minus 1. And that's just a notational thing, because when we look at both of our functions, the input for both of our functions is now named x. It's just that the input for one function is the output for the other function and vice versa. So yeah, that's a little bit confusing. So here's another method. This is a more usual way of doing this. So a usual approach is to actually swap x and y, then solve for y. So what that would look like in this example, originally we have y equals x plus 1. When we swap, we have x equals y plus 1. We subtract 1 from both sides, and we have x minus 1 is equal to y. That looks like a g. X minus 1 is equal to y. And that is what we take to be f inverse of x. Okay. So again, the notation's a little bit funky, but that is what's going on. So overall, f inverse of x is x minus 1. So that is the inverse function to x. Let's see another example, because this process is a little bit complicated. Here is a more complicated function, f of x equals 1 plus 1 over x. I've graphed it so that we can see, again, this function passes the horizontal line test. It also has a vertical asymptote and a horizontal asymptote. So this f passes the horizontal line test, so f is 1-to-1. So if we want to compute f inverse of x, Again, I really prefer to swap my x and my y and then solve. It's less confusing that way. So originally, we have y equals 1 plus 1 over x. So this is the original function f that we have. We swap. We have x is equal to 1 plus 1 over y. And now we're going to solve for y. The first thing that I can do is subtract 1 from both sides. So I have x minus 1 is equal to 1 over y. Now I can cross multiply. So I think of x minus 1 as being over a 1, and I can cross multiply. So I have y times x minus 1 is equal to 1 times 1. I can divide through by x minus 1, and I end up with y equals 1 over x minus 1. And now this, once we're done solving for y, we have our new f inverse. So all in all, the inverse function is 1 over x minus 1. So this example, it's nice to see that you can't just swap addition and subtraction in order to get an inverse. You really do have to do this algebraic simplification. Okay, so when I told you what an inverse was, I gave you a very intuitive notion of what an inverse was, and now we've seen a way to compute these algebraically. So let's see a rigorous definition of what it means for two functions to be inverses. So I'll read through this and then I'll explain it. If f and g are functions such that if I take f and I stick it inside g, if I have g of f of x, it simplifies to just the expression x. And if I do that the other way, then I get back to x itself. So the idea behind this is that x gets sent to some y value by f, which gets sent back to the original x value by g. And likewise, x gets sent to some y value by g, and then gets sent back to the original x value by f. And so each of these functions undoes the other function. When I stick one inside the other, when I do one followed by the other, I get back where I started. So let's look at example 1. I computed algebraically that f of x equals x plus 1 has inverse g of x equals x minus 1. And now I'm going to show that this funky calculation that I did, swapping the variables and solving, is actually correct. So if I take g and I stick in f, so this is going to be g of x plus 1. My rule of g is to take my input, so take x plus 1, and subtract 1 from that. That's my rule g. So I have x plus 1 minus 1, which is just x, and so I do get that g of f of x is just equal to x. So that's one half of the definition. I want the other half of the definition, f of g of x. So I take f and I stick in the function x minus 1. And my rule f says I take my input, x minus 1, and I add 1 to it. So now, if I simplify that, I have x minus 1 plus 1. That simplifies to x, and so overall I have that f of g of x is equal to x as well. So these were these two parts of this definition that we need. And this is a nice easy example because you can see, yeah, adding 1 and subtracting 1, they undo each other. So we are justified when we say that g of x equals x minus 1 is f inverse of x. So there's two different parts of this. There's figuring out what the formula is for g of x, and then there's also showing that that actually is the inverse. Now let's practice this algebraic verification one more time. So in our more complicated example, we had that f of x was 1 plus 1 over x, and we computed that its inverse was 1 over x minus 1. And it's less obvious in this case that g does undo f. So let's compute g of f of x. So again, I'm taking g and I'm sticking in the entire function f. And my rule g is I have 1 over my input minus 1. So when I simplify that, I have 1 over 1 plus 1 over x minus 1. So I have 1 over x. And when I have 1 over a fraction, I can multiply by its reciprocal. And so I do indeed get x. So again, what I showed is that g of f of x is equal to x. That's half of it. We have to do the other direction, so let's look at f of g of x. So I take f and I stick in 1 over x minus 1. So my rule f is to take 1 and add 1 over my input. Again, I'm dividing by a fraction, which is the same as multiplying by the reciprocal. And so this simplifies to 1 plus x minus 1, and those 1's cancel, and I just get x. So again, what I showed is that f of g of x is equal to x. Because both of these things are true, the inverse of x is g of x, which is 1 over x minus 1.